Welcome to Lecture Online, and by special request from some of the viewers, we're going to do some more problems on finding the electric field on various kinds of situations. A lot of them are going to be like charge distributions, but here I thought I'd throw in the electric dipole, because that's a common thing in physics, and so we should know how to do that and how to find the electric field of an electric dipole. What is electric dipole? Electric dipole is two charges that are equal in magnitude but opposite in sign that are very closely spaced together. So they're very close, and we want to find the electric field at some point along the what we call perpendicular bisector. So what we find is we find the halfway point between the two charges, which is right here. We draw a line perpendicular to that line, and then we want to find the electric field somewhere along that line. So we're going to do things kind of in a general sense, and then when you throw numbers in there, you just kind of do it exactly the same thing but with numbers. All right, so what do we do here? Well, you can see here that based on this chart right here, we're going to have an electric field that emanates in this direction, and so we're going to call this port right here the electric field at this location due to this positive charge. Then we know that for negative charges, electric fields are directed towards the charge. So the electric field at this very same location due to this charge is in this direction. And so the total electric field experienced by both of these charges at this location will then be to the right, which is simply a vector sum of E1 and E2. I call this charge 1, I call this charge 2, as denoted, notated right there. Notice the difference between the charges is d, therefore x is half the distance between them. The distance from the line connecting the two charges to the point of interest right there is a, and so that makes this distance right here from that point to this charge and from that point to this charge, that is equal to the distance r. Okay, now the general equation to find the electric field due to a point charge is this. Electric field is equal to k times q, the charge that causes it, divided by the distance from the charge to the point of interest, r, and we square that. So that's the general equation. So to find E1, we can say that E1 in this case is equal to k times q divided by r squared, and we can say that E2 therefore also is equal to k times q divided by r squared. Now notice that I did not put the negative in there because I didn't care about the direction, I only care about the magnitude of E1 and E2. Now, in order to add those two, I can see that the vertical components of E1 and E2 are simply going to cancel each other out. Notice that if I draw that, let me use some green here. So here you can see that would be the horizontal component of E1 and the vertical component of E1. Here's the horizontal component of E2 and the vertical component of E2. And notice that because of their distance from that point to each of the charges is exactly the same, and the size of each charge, the magnitude of each charge is exactly the same, except one is positive, one is negative, you can see that the vertical components should be equal in size and therefore cancel each other out, and the only surviving components are the two horizontal components which we need to add. So how do you find the horizontal component of E1 and E2? Well, if I assume that this here is the angle theta, I can then see that this here is the angle theta as well, and then here this should be the angle theta as well. So that way we can see that the horizontal component is simply going to be the magnitude of E1 times the cosine of that angle. So we could say that E1 in the x direction is equal to E1 times the cosine of theta. Now remember, the definition of the cosine of any angle is the ratio of the adjacent side divided by the hypotenuse. So if we look at this angle right here, which is the same as this angle there, the adjacent side would be x and the hypotenuse would be r. So that means it's equal to the ratio of x divided by r, and I can then replace the cosine of theta by the ratio of x over r. Now also, in this particular picture, I can also say that r is equal to the square root of the adjacent side squared and the opposite side squared right here. So it would be x squared plus a squared. A, of course, is simply the distance from the bisector, not from the bisector, but from the line joining the two charges to the point of interest. All right, so if I then plug that in here, notice that E1 in the x direction is equal to E1, which is k times q divided by r squared times the cosine of theta. Now I can replace r squared by this right here. So if I square r, I get this quantity squared, or simply what's underneath the radical. So this is E1x is equal to k times q divided by, let's see here, x squared plus a squared times the cosine of theta, which is x over r. So that would be x divided by r. And then again, this r can be replaced by this right here. And so we then get E1x is equal to k qx over x squared plus a squared. And the whole thing multiplied by the square root of x squared plus a squared. So finally, if I combine those two, when I multiply them out, I get the denominator raised x squared plus a squared raised to the 3/2 power. And so what I can do here, I can then say that E1x, I forgot my 1, I was already writing the x. So E1x is equal to, right here we have k qx divided by this quantity right here, x squared plus a squared to the 3/2 power. All right, so that's E1 in the x direction, and because of the symmetry here, we know that E2 in the x direction should be the exact same amount. So we can say that E2 in the x direction, therefore, also is k qx divided by x squared plus a squared to the 3/2 power. And then, of course, we can then see that E is simply the sum of the two x components. So E is equal to E1x plus E2x. And so therefore that's equal to twice this number. So 2 times k qx divided by x squared plus a squared to the 3/2 power. Now, going back to what x was equal to, remember that x was just half the distance between the two charges. So with other words, we could say that x is equal to the distance between the two charges divided by 2. And most likely, when you work with dipoles, you want to express the answer in terms of the distance between the two charges, not half the distance between the two charges. So we're going to replace the x by distance over 2 and x squared by distance over 2. So what we'll get there then is that the final answer will be, well, not quite, almost there. 2kq times d over 2 divided by d over 2 quantity squared plus a squared to the 3/2 power. And finally, you can see that the 2's cancel out. And so finally, you can then write that this is equal to k q d divided by d over 2 quantity squared plus a squared to the 3/2 power. And now we have the magnitude of the electric field caused by dipole when the point of interest is right along the perpendicular bisector between the distance between the two charges. So, if you now want to write it in a vector format, well, in this particular case, since E is to the right, you can then say that the vector E is equal to the magnitude, which would be k times q times d divided by the quantity d over 2 squared plus a squared to the 3/2 power in the positive x direction. So we can use x hat or I hat, whatever you prefer there. All right, so now notice, for those who look at it and go, well, wait a minute, what is k again? Remember that k is equal to 9 times 10 to the 9th, and that would be newtons meters squared per coulomb squared. So that's the constant that comes out of Coulomb's law. Q is the magnitude of the charge. D is the separation distance between the two charges. A is the distance from the line connecting the two charges along the perpendicular bisector to the point of interest, where we want to know the electric field. And that's it. That's all you need to know. There's the answer. So that's how we write it in vector format.